All right, so today we're going to talk about three concepts related to population genetics as described last week. And at the end, we can have a Q&A. So the first one, which is a very important concept, is the mutation selection balance. What is the idea? The question is, as we know, now that we have moved on from Hardy-Weinberg equilibrium, where you have no fitness difference between different genotypes, in the case of mutations, we have fitness effects. And indeed, we can imagine a scenario. Again, we're using the two allele, two locus scenario. So we have A1A1, A1A2, and A2A2 as three genotypes. A2 as three genotypes. And let's say A2 is deleterious. So the fitness values of, so if it's simply recessive, it means that W11 and W12 they are the same, but W22 has the lowest fitness. Or if it's lethal, then it means that W22 is dead, right? And these are only the recessive cases, right, where A2 allele, so the A2 allele that is the deleterious allele is recessive, so the heterozygotes, they don't show the problem. Now the question is, given that there's a persistent selection against the A2 allele, given its disadvantages, fitness consequence, then why do we see A2 allele in the population? Anyone has any suggestion on why do we see A2 allele in the population at all? Just to simplify, let's add let's limit ourselves to a third scenario in which A2 is actually, because you might say that all heterozygotes are going to exist anyway, so A2 can exist that way. Let's say A2 is dominant and is lethal, right? So let's just talk about this case, this one. So in this case, it's obvious that A2 is an extremely, I mean, it's a lethal allele, but it's lethal and is dominant, so it should be pretty easy for selection to just simply purge A2 from the population, right? Because any genotype carrying A2 is going to be dead. So why would you find, so in a real life example, that would be something like Huntington's disease, where the disease in question is actually a dominant allele. But the question is, why do we see Huntington's disease in real life? Why don't we see that dominant deleterious or dominant lethal allele persisting? So anyone, any suggestion, just type it in. Any way you would think would result in this lethal allele to stay in the population. Anyone? Okay. Bilal says no alternate allele in the population. So the only alternate allele is A1. So we have A1 and A2, and the question is, why don't we end up with A1? So A1. So the allele frequencies, as usual, we use P and Q. So if I were to draw the plot for P, which would be the allele frequency for A1, right? So that should be A1 allele frequency over time. My question is, why doesn't it just go up like this and stay at 1? So let's say here is 1. So why doesn't all the why isn't only allele in the population just A1? So anyway, we can do that. We can retain A2 despite of its lethality, as we have established. Anyone? So first of all, if we have purely Jennifer's mutations, of course, which is the correct answer. So in the case of lethal or deleterious alleles, if you simply have selection, then the allele frequency should decrease over time by this factor. So the delta, let's call it delta S. So it's the change in allele frequency of Q. Sorry for the handwriting. I'm writing with a mouse, so it's not really great. But it's see the point. So over time, the allele frequency of Q should decrease like this. So if we were to plot T, so if we were to plot Q over time, it should decrease according to this this slope. So this one is the rate at which we're going to have a decline. So if we have, let's say at the beginning 50% RQ, it's going to go down, down, and eventually 0 according to this slope, right? So that's where, when you have no mutation whatsoever. If you had mutation, you're going to have a change. You're going to have a different source of Q, which is not going to be negative. So in the case of delta SQ, which I have written here, in this case it's a negative change, a negative delta Q, but we can have a positive one, which would be delta, let's call it delta M Q. So it's the number with the Q, the change in frequency of Q as a function of mutation, where there is a mutation rate U, which converts the A1 alleles into A2. So mu or U multiplied by P. That's so the mutation rate multiplied by the frequency of A1. And what it does is it converts A1 into A2. So you have A1 turning into A2 with a probability, or with the rate mu. So then, given that you have frequency P, A1 in the population, at each generation you're going to have P multiplied by U, which is the mutation rate of this one directional mutation rate from A1 to A2. That amount is going to be a result in Q. So Q is not going to go to 0 because there is a positive. While there's a positive, there's a negative. Sorry, so this delta Q is negative. So it results in Q going down. Delta MQ is positive because it's an increase in frequency of Q. So it's going to increase Q in the population, hence making it stay within the population. Now there are different possibilities. We don't need to know the proofs of it, of how you get these equations, but depending on what type of mutation A2 is, so is it deleterious, is it lethal, is it recessive or dominant, we are going to have different combinations, different expectations of Q, so the definition of Q at equilibrium, so Q with this hat, which denotes Q at equilibrium. So you can have, let's create a table. So we can have when, first of all, we can have two different situations where W22 is non-zero, so this is so it's deleterious but not lethal. But in another case, W22, so the phenotype carrying both A2 alleles is lethal. Now, in the first case, we can have dominant or recessive. So let's divide it into two parts. So in the case of, so let's say this one is recessive, and this row is dominant. So in the case of recessive, the frequency of Q at equilibrium is going to be proportional to the square root of mutation rate. Actually, let's use real fonts. That would be better. So that would be mu. That would be U mutation rate divided by 1 minus W22. In the case of so it's so in the case of lethal, this equation, so the square root of U over 1 minus W22. In the case of lethal, of course, W22 is 0, so it's 1 minus 0, which is simply 1. So that would be simply the square root of mutation rate. In the case of dominant, the square root part is going to disappear. So in the case of dominant, deleterious is going to be simply U over 1 minus W22, which is the fitness of the genotype carrying only the deleterious allele. And in the case of lethal, W22 again is 0, 1 minus 0 is 1, so it's just going to be equal to mutation rate. So as you can see, in all the cases, it is proportional to mutation rate, but in the case of recessive ones, there's a square root added to the equation. So any questions so far? Any question about mutation selection balance before we move on to drift? All right, so let's go to genetic drift. Now, drift is usually described, can be described as a force that acts against selection. There's a long history of people in biology using physical terms to describe biological mechanisms, and there has been actually a long tradition of criticizing that, like treating selection like a selective, describing selection as a selective force, or drift as a force is kind of confusing because it's not like gravity or anything like that, but and it doesn't have the physical connotations, but it's kind of simple and a little bit lazy to use, so I'm going to stick with the same terminology. So that's the most important thing you have to know about drift is the way it interacts with selection. Um, the way selection and drift. So because usually whenever you deal with a population, um, or you want to study the population genetics of a system, you need to understand that unless it's an infinite-sized system where there's no real population size, in that case there is no drift really. Drift comes from the idea that whenever you have a population, and what we're doing is usually described as a Wright-Fisher model, which is Fisher, which is a simple model where you have parents and you create offspring. So you have a generation. So let's say this one is generation 1. We want to create the second generation, and we keep the size the same. So in this case, let's say we have, let's use alphabet to show the individuals. So we have A, B, C, C, and D. So we have 5 individuals in one generation. We want to have 5 in the next. And what Wright-Fisher model does is to, I'm skipping the selection bit. So if the fitness values are different between A, B, C, and D, then they're going to be selected according to their fitness values. So if you are dead, if you have a lethal mutation, you can't be picked for the next generation because you can't reproduce really. But even if the fitness values there are no lethal alleles, only deleterious ones. Again, if you carry more deleterious alleles, you are going to have less chance of getting picked. But for the sake of comparison here, just the simplest scenario would be picking individuals here where everyone has the same fitness value. So in the next generation, I just pick at random, and I can end up with something like this. Right. So it's a new configuration of alleles, right? And let's say in the next generation, just to show you what's going to happen. In the third generation, again picking according to, assuming that they all have the same fitness, let's see. Okay, there's some, I can actually use the same scenario to explain several different ideas related to drift. First of all, as you can see, the change in frequencies. So at the beginning we had A, B, C, and D, so 4 different types, and we had 5 individuals in the population. In the second generation, we have 3 types, and in the third generation, we have only 2 types, right? So that's fine. But the other thing is that the process that we used to create the next generation was simply a random process. So we went through the individuals in the population and picked individuals at random, without really, as long as they were alive, we just picked them. Right. Again, if we had fitness differences, it would have been the sampling process would have been a weighted sampling, where you would have picked according to the fitness as well as frequency. So the first thing, so this is genetic drift. This process is a sampling. And it is a random, the term uses stochastic, which simply means just random. And the main animosity, if we were to anthropomorphize these different forces, the animosity between drift and selection comes from the fact that selection is anything but random. Selection is a non-random process. Non-random. Or you can call it deterministic. Right? So the main problem in population genetics, or the main problem to be solved in every case, is to see how strong is drift versus how strong is selection, and how the interaction between the two results in the change in allele frequency, right? So what we're interested in is the way different alleles change in frequency when they are neutral and when they are beneficial or deleterious. In the case of a neutral allele, a neutral allele, of course, has no fitness value, really, no fitness consequence, rather. And if we had a population, a diploid population, right, and we had a new mutation that resulted in a neutral allele to appear in the population, the frequency, the initial frequency of that allele would be 1 over 2n, right? So the population is diploid, so everyone carries 2 sets of chromosomes. On each set there is one copy of alleles, and there are 2 in every individual. So you have a pool of 2n genomes, and when you have a new mutation, that is 1 over total number of genomes, which is 2n. So the frequency when an allele appears is 1 over 2n. The probability of this allele going to fixation, and fixation simply means something like this. So if we were to look at the frequency of the alleles, in this case, let's say the frequency of this one is p, over time, right? So p is, in this case, is a mutation, right? So at the beginning it's 0 as long as it doesn't exist, and then at one point you have a frequency of 1 over 2n, right? So it's 0, 0, and it becomes 1 over 2n at some point. And over time, it can go up to become 1, so meaning that everyone in the population carries that allele. So here is the ceiling, which is 1. So when the frequency of the allele is 1, it simply means that everyone carries the same allele. Now, given the frequency, what is the probability of this allele going to fixation? Again, as described here, fixation is the allele frequency going to 1, where that allele becomes a wild type allele where everyone has it. So what's the probability of that, given that the frequency is 1 over 2n? Anyone? Any suggestion? So what is the probability of fixation for this neutral allele? First of all, what force is going to result in the fixation of this allele? Is it going to be selection, drift, or both? Anyone? Just type it in. So the first part of the question is how is the way this allele is going to increase in frequency and go to fixation? What evolutionary forces are going to act on that process, on the fixation? Is it going to be drift alone, selection alone, or both? So Jennifer and Bilal, they both correctly pointed out it's going to be drift. Why is that? Because it's a neutral allele, so it's neither deleterious, certainly not lethal, and it's not beneficial, right? So selection has no stake in this allele spreading in the population, right? So it's a toss-up for as far as selection is concerned. But drift can result in the fixation. Now, since the frequency is 1 over 2n, the probability of you picking it up, so as I described in the Wright-Fisher model here, where we sample from generation 1 to generation 2, and the sampling is simply picking individuals from the parental generation and creating the offspring, the next generation based on that. The frequency of us picking this new mutation, this neutral mutation, is 1 over 2n. So probability of fixation is also the frequency of the allele in question, right? So 1 over 2n is also the probability of fixation, as well as the frequency. Clear so far? So for a neutral allele, genetic drift is going to act on the allele, and the probability that the allele in question would go to fixation is simply its frequency. Now, in the case of so the example I have drawn, where we have generation 1 and the second generation and the third, what happens to genetic diversity as we generate the next generation over and over again? So where do we have the highest genetic diversity between these three stages? So does 1 have the highest, or 2 or 3? Anyone else? Jennifer just answered. Anyone else disagreeing or agreeing with that? So in the case of Christina also pointed out this, in the first generation, we have A, B, C, and D. So we have 3 types. In the second generation, we have so in the first generation we have 4 types, A, B, C, and D. In the second generation we have 3 types, and the third we have 2. Now I did that intentionally because it turns out that so that there's an observed level of heterozygosity, which is simply the frequency of heterozygotes, right? And that's in the case of the 2 allele 2 locus system. And in the case of Hardy-Weinberg, you have an expectation which is 2pq, right? And Hardy-Weinberg, as we know by now, is simply based on infinite-sized populations. It's not really realistic for natural population. It turns out that in natural populations, heterozygosity, which in the next generation, H prime equals to 1 minus 1 over 2n. So 2n is for diploid organisms, so that's why it's 2n as opposed to n. Now, so it simply says that so if the population size is too big, right? Would heterozygosity change a lot? So when the population is huge, would the heterozygosity change dramatically, or would it change in a non-significant manner, in your view? So so given a large population, would heterozygosity change quite a lot each generation, or would it change a little bit? Now Christine says a little, Sarah says a little bit, Kaza says a little bit, Kaza says not so much, consistently. Why is that? This is simple mathematics, right? Because h is multiplied by 1 minus 1 over 2n, so as 2n increases, 1 is going to be subtracted by an increasingly smaller number, so the change is going to be more insignificant. And in the case that I showed you, in a scenario where we have 5 individuals, the change in allele frequency, or the gene diversity, heterozygosity, has been quite dramatic because we went from 4 types to 3 to 2, and that's actually conceivable given the population is so little. If you had instead of 5, 10,000, and then the frequencies in the next generation would be or would have been more representative of the previous generation. Now it turns out that this decline in frequency, as again pointed out by a few of you, is going to be more dramatic. So if we have heterozygosity on heterozygosity on one in y-axis and time on the other. So for as we decrease the population size, the allele frequency, the decline in heterozygosity increases as well. So the population size in these 3 trajectories, as you go up, you get to a bigger population. All right, so the change in heterozygosity is going to be more dramatic as the population size decreases. Now, this is interesting because it turns out that sometimes when you measure the decline in heterozygosity, so let's say we had, let's say the last trajectory, so let's say this one is for population. Okay, this sometimes is a little bit funky. Why is it doing this? No. Okay. Sorry for the delay. Sometimes I have to wrestle with this software to make it do what I want to. It's not a very well made software. I mean, it's Adobe, and they don't really think with anyone, so it doesn't matter to them to make it better. So let's say the latest the trajectory is for a population of 10, right? And the question is, sometimes when you go to in the wild and try to measure the decline in heterozygosity in a real population, let's say you work on Drosophila and you looked at the heterozygosity over time, and what you measured looks like a population where, so let's say the real data points you have are these, and here and here. These red dots are the real data points. And what you see is that, okay, this looks like a population size of 10, but when you actually measure it, let's say it's n equals 15, right? So what's the problem here, really? This is where the concept of effective population size becomes useful. So in the case of population that you have been observing, the Drosophila, since the decline in heterozygosity matches the expected trajectory for a population of 10, you can say that the effective population size of the experiment is 10. So this Drosophila population they have an effective population size of 10. So that is the formal definition of effective population size. So a population that shows the same declining trajectory as the as expected from a Wright-Fisher model, right? But now the question stays is still relevant, which is why do we have this discrepancy? Why do we have more individuals in the population, but we divine fewer individuals or a smaller population from the decline in heterozygosity? Now there are different ways, different reasons for it, but the simplest case, which is relevant to all the reasons that result in this discrepancy, is that not everyone in the population reproduces. So in the case of a Wright-Fisher model, we assume that everyone in the population reproduces, and the ratio between sexes is 1-to-1. So in these models, we simply have two genders, or two reproductive units. We have males and females, and not necessarily true in every, of course, organism. In a lot of protozoans, there are like 5 or 6 different sexes. In this case, in the simple standard Wright-Fisher model, we have male and female. And what they assume is that if you have a population size of 100, not only everyone is going to partake in reproduction, you also have, in the population size of 100, you have 50 males and 50 females. And so there's no surplus of one sex relative to the other. Now, when you look at a real population, of course, that is not the case. In a real population, first of all, not everyone is participating in reproduction. So you have age structures. So, for example, in human population, you have people between, let's say, in Western world would be between, 18 to 40, where they actually reproduce. People younger, they don't, and hopefully they don't. And older, they really can't do that. And most of them, they can't do that. Although that differs between males and females. So you have a subset of population that reproduces. And even in the subset, you don't have equal numbers of males and females. It differs between different countries. Like the most egregious ones are, I believe, India is the worst one when the population is very unbalanced. So you have too many males and too few females. And that, again, results in having a different effective population size relevant to the actual population, the census population size. What is the actual number of individuals versus the number of individuals that do participate in reproduction. So that is the change in heterozygosity. Sorry, well, one more thing actually. The Wright-Fisher model also assumes that the population size stays fixed. That is not the case, right? So you can't really assume that. In a lot of populations, the population size changes over time. And in order to take that into account, so you can use the harmonic mean. So if we want to calculate the effective population size, we can, actually, let's just use, okay. So it's time t, so let's use the, okay. So we have time t, we have, why is it so 1 over n at step 1 plus 1 over n at time 2 until we reach 1 over n times t. Does anyone know why do we use this method to calculate mean? Why not just calculate the mean in a simple arithmetic way that is not harmonic, just a simple mean of these population sizes? Why do we go to why do we take the trouble of having this kind of unusual calculation in order to take into account the change in population size? Does anyone know that? So the question is why do we calculate the mean when the population size changes this way, also known as harmonic mean? Why don't we just calculate the mean in the simple way that you would have had you not known that this is the correct answer? Anyone? Nope. Okay, so the reason for it is population size. Harmonic mean is more sensitive to smaller population size or smaller values in general as opposed to the normal mean. And since drift is driven by the very small, or is more effective when the populations are pretty small, we need a measure of mean which would take that into account. And harmonic mean would take that into account and allow us to have a sensitive measure of population size, mean population size over time, where a smaller population size is going to be influential. All right, the last thing I want to talk about is the question, the same way that we asked about the same question we asked about deleterious and lethal alleles. The question that, given the lethality or the deleterious nature of these alleles, why do we see them persist in the population? So now, looking again at the example of these 3 stages, the first, second, and third generation in this Wright-Fisher model, we see an obvious decline in heterozygosity. The question is, why do we have heterozygosity to begin with? So the populations that we look at right now in nature have been evolving for a long time. Why is there gene diversity at all? If the diversity is going to decline over time, as drift gets rid of a lot of or drift decreases heterozygosity, why do we have heterozygosity at all? Anyone? So again, given the effect of drift on heterozygosity, which results in its decline, why do we have heterozygosity in populations? Just type in your answer. Anyone? Why do we have heterozygosity, given drift is doing what it's doing? Bill Alice says, can it be caused by selection? Just assume that all of them are neutral alleles. So let's not, let's say that they have no selective advantage or disadvantage. So is heterozygosity purely based on neutral alleles? So if they disappear, it doesn't matter really. Recombination, Christine says recombination. And recombination is going to, is recombination, well, let's say, Christine says recombination, but so let's look at the population, the second generation and the third generation, right? In this third generation, we have A and C. If they recombine, given that, so in this example, all of these individuals are haploid, Just for simplicity, I made them so. So if A and C combine or recombine, they are not going to create B again. So because that allele is gone, so recombination is going to reshuffle existing alleles, but it's not going to create new alleles, right? So not recombination, but there's another biological process that is similar to recombination that results in having new variation. What is that? So where does variation come from, given this drift thing? So there's something that is kind of is usually mentioned whenever someone mentions recombination. What is that process? So let's make it easier. So in the population, in the third generation, how can I turn A into B? Like, what would allow me to get B again, given that B doesn't exist in this population? Mutation, yes, Kristen is right. Mutation, yes. So even though a lot of heterozygosity is going to be gone, a lot of alleles are going to be gone in smaller populations, or even in a very large population, over time, you're going to have a decline in heterozygosity. Mutation can create new alleles. And so the same way that we had mutation selection balance, we can have a mutation drift balance, where drift gets rid of alleles and mutation reintroduces them. All right, I think by this point I've covered the topics from last week. If you have any question from last week, please feel free to ask them right now. We are at the Q&A section of this recitation. Can we go over homework 6 question? Where is actually homework 6? Homework 6 question 4. Let me find that. Okay, go. Oh, sorry. Yes. A question. Jennifer asks, "Can we go over homework?" Yeah, that is a question actually which I couldn't correctly answer on the last recitation. Actually, I haven't tried to find an answer yet. My apologies. I will go over this on Monday, showing what exactly is the correct answer. Again, sorry, I didn't prepare one for today, but I totally forgot that. Just writing my thesis and everything. It's a little bit. Yes, on Monday I will cover that question. Please remind me on Monday to do so, because I should have done it today, but I totally forgot that. Yes, and as you pointed out, we tried it on Friday. Jennifer said I only go to Tuesday recitation? There's a recitation on Tuesday? No, it's Thursday. Yes, okay, so it doesn't matter. So I give the answer on Monday, and I'll have the answer on me on Thursday. So if you order, I'll just explain it to you as well. So that should be fine. Any other question? Any question, comment, concern? So again, you can simply just type the questions, or or talk. I mean, no one has tried to talk for some reason. Uh, Probably for obvious reason. I'm not sure. Uh, People are not prepared to take that risk. Mhm.